This is mathematical models and numerical methods involving first-order equations, and we will be talking about Newtonian mechanics. And Newtonian mechanics is the study of the motion of ordinary objects. So nothing too small like atoms, nothing moving too fast like the speed of light. So we're going to go ahead and take a look at Newton's second law of motion. As you can see, we have, of course, force equals mass times acceleration. And here our force is dependent on time, location, and velocity. However, in this section, we are going to focus on situations where the force does not depend on x. So it does not depend on location. Which would be x, okay? And so this is what we're going to focus on in this section. Okay, so let's go ahead and take a look at what we have. And we can look here over at this diagram here. And as you can see, we will have an object of mass m. And this is given an initial downward velocity right here of v naught, and it's allowed to fall under the influence of gravity. So as you can see here, the force due to gravity here is F sub 1. So you could say that this is F sub 1. And F sub 2 is going to be the force due to air resistance. And of course, this air resistance acts in opposition of the motion of the object. So that is why, of course, we are using a negative there. Okay, so now as you can see, we have an initial condition and we have a differential equation. So we now have an IVP. And let me go ahead and square that off. Okay. And now we can take a look at our solutions, our velocity at any time of the object, and the location at any time. Now this velocity you could have found using separation of variables to come up with the velocity. And then of course we can integrate the velocity and come up with our x of t function. So both of those we will also be using. So let's take a look at both of these functions as t approaches infinity. So as you can see here in this diagram, taking a look at the velocity, v of t will approach this horizontal asymptote, v equals mg over b. So here, this velocity will approach mg over b. So let's write that down. The limit as t approaches infinity of v of t is equal to mg over b. And as you can see, of course, this term would go to 0 when we take that limit. Okay, And so this mg over b, this horizontal asymptote, is also called the limiting or the terminal velocity. So let's write that down. It's the limiting. It can also be called the terminal velocity of the object. Okay, so now let's take a look at our x of t function as t approaches infinity. We can see that the position x of t asymptotically approaches this line. And let's go ahead and write that down. So we have the limit as t approaches infinity of x of t, and that's going to be equal to mg over b multiplied by t minus m squared g over b squared plus m over b v naught. And you can see that, of course, when we distributed this m over b, and this term went to 0, and we still had the 1. Okay, and so we can see here that this here is the line that x of t approaches as t approaches infinity. I do want to make a note that the velocity of every free-falling body, let's make a note. Note, the velocity of every free-falling body approaches the limiting velocity. Okay, let's take a look at our first example. We have an object of mass 3 kilograms, and it is released from rest 500 meters above the ground and allowed to fall under the influence of gravity. We will assume our gravitational force is constant, 9.81 meters per second squared, and the force due to air resistance is proportional to the velocity of the object. And here we are given our proportionality constant as 3 Newton seconds per minute. Here in this problem, we will find when the object strikes the ground. We will use our model for x of t here and go ahead and write down a few bits of this information from the problem. We have v naught is equal to 0 since it was released from rest. We have the mass is equal to 3 kilograms. We have B is equal to 3. And we have, of course, gravity is equal to 9.81. So from our equation, we have x of t is equal to 3 multiplied by 9.81 divided by 3 times t minus 3 squared times 9.81 divided by 3 squared multiplied by 1 minus e to the negative 3t over 3. And we will come up with 9.81t minus 9.81 multiplied by 1 minus e to the opposite of t. And you can, of course, see that here, see that here, and see that here. Okay. Now, since the object was dropped from 500 meters above the ground, we can go ahead and set x of t equal to 500. And go ahead and solve for t. I'm going to distribute that 9.81. And as you can see, we cannot solve this equation explicitly for t. There are some other approximations that we can come up with, but we can go ahead and ignore this term. It is going to actually be very small, and this would be very small when we find our t. Let's see how we come up with that. So let's go ahead and solve this first before we include that. So adding 9.81 to both sides, and then going ahead and factoring out a 9.81, and then having 509.81 divided by 9.81. And as you can see here, and this was supposed to be a t and a t. So taking a look at this, you can see that t minus e to the opposite of t, and I divided that 509.81 divided by 9.81, come up with 51.97. So if we ignore this and we let t equal 51.97, what we will see is that e to the negative t, when t is equal to 51.97, is negligible. So we will ignore that, and we do obtain our approximation that t is approximately 51.97 seconds. And that is when the object will strike the ground. Let's go ahead and take a look at our next example. We have a parachutist whose mass is 75 kilograms. And the parachutist drops from a helicopter hovering 4,000 meters above the ground and falls towards the earth under the influence of gravity. Assuming the gravitational force is constant, we will assume that. We will also assume that the force due to air resistance is proportional to the velocity of the parachutist. And we do have a proportionality constant of 15 when the chute is closed. And we have a constant of 105 when the chute is open. If the chute does not open until 1 minute after the parachutist leaves the helicopter, after how many seconds will she hit the ground? So taking a look at this, we are going to take a look at the motion before the chute opens, and then to the other, we will apply that information to when after the chute is open. So before the chute opens, the model is pretty straightforward. Let's go ahead and write a few things down. We have the initial velocity is 0, mass is 75 kilograms. B is equal to B1, which is going to be 15, of course, Newton second meters. And then, of course, we're going to be using gravity, 9.81. So we are just going to be working with the vertical distance because we just want to know when she hits the ground. We are not concerned with where she hits the ground. So we will not have to do anything but only take a look at the vertical component. We will be using 1 for before the chute opens. So we'll go ahead and plug these into our equation for v of t and also for our location x of t. So we have 75 times 9.81 divided by 15 plus our initial velocity is 0 minus 75 multiplied by 9.81 divided by 15 multiplied by e to the opposite of 15 times t divided by 75. And we can come up with, if we simplify that, 49.05 multiplied by 1 minus e to the negative 0.2 t. Doing the same thing, we'll go ahead and have that position at any time t before the chute opens, and plugging those values in, we will have 75 multiplied by 9.81 divided by 15 times t plus 75 divided by 15 multiplied by 0 minus 75 times 9.81 divided by 15 multiplied by 1 minus e to the opposite of 15t over 75. And simplifying that, I came up with 49.05t minus 245.25 multiplied by 1 minus e to the opposite of 0.2t. So let's see what happens at 1 minute. So after 1 minute, that is when t is equal to 60 seconds. The parachute is falling at a rate of, and so let's go ahead and plug 60 into V1, and that is 49.05, 1 minus e to the negative 0.2 times 60, and that is equal to 49.05 meters per second. And how far has the parachutist fallen? So after 60 seconds, let's go ahead and find the location. 49.05 times 60 minus 245.25, 1 minus e to the negative 0.2 multiplied by 60, and that is 2697.75 meters. And I will be rounding to 2 decimal places. So now the chute opens, okay? So once the chute opens, the parachutist is located, and let's go ahead and take care of that. So we will have 4,000 minus 2697.75, and the parachutist will be 1,302.25 meters above the ground. and will be traveling. And let's go ahead and note that it will be traveling at that velocity, 49.05 meters per second. So now we know what happens before the parachute opens. Now let's talk about what happens once the parachute does open. Okay. Okay, so the first way we're going to do is we're going to let capital T equal T minus 60. And the capital T is the time after the parachute opens. So now we have that x2 of t is going to be the position of chute after, that would be parachutist, position of parachutist after the chute opens. Okay, so we have x2 of 0 is going to be equal to 0, and that's going to be at the same place x1 is equal to 60. So let's go ahead and draw a little diagram. So we have, I will pause the video and draw this. So we have t equal to 0, and here we have the parachutist, and here is our first x1 of t. This is prior to the chute opening, and here we can say that the chute opens, and here is that distance we came up with, 2697.75, and that will go right here, and then that remaining is 1302.25, and that is to the ground. So now this is where we are saying capital T is equal to 0. It's also where we're saying x2 of 0 is going to be equal to 0 at x1 of 60. Okay, and then this second part is going to be x2 of capital T. So that will be that location at any time, capital T. Okay, so let's go ahead and continue on. We are going to use our same equations that we used before, x2 of t, and we're going to have 75 multiplied by 9.81 divided by 105, and that's by multiplied by time capital T plus 75 over 105. And here now we have our velocity right after the parachute opens of 49.05 minus 75 multiplied by 9.81 divided by 105, and we have that multiplied by 1 minus e to the negative 105 t over 75. Okay, see if I can make that just a tad bit smaller. Okay, and coming up with that in a simplified manner, we have 7.01 t plus 30.03 multiplied by 1 minus e to the negative 1.4 t. Okay, so now we need to determine when the parachutist will hit the ground. Okay, so and that's when we're going to set x2 of t equal to 1302.25. That is this distance right here to the ground. So how long does it take to travel that distance? Okay. And so, simplified, we come up with t minus 4.28 e to the negative 1.4t minus 181.49 equal to 0. So if we go ahead and ignore this exponential term, we can see that t is equal to 181.49 seconds. Now, I want to make sure you understand that this is negligible. Let me put a little star here. Whoops. And I'll write that over here when we can say that e to the negative 1.4t is very small when t is close to 181.49. So we will go ahead and ignore that. So the parachutist will strike the ground 181.49 seconds, and this is after the parachute opens. And so, or we could say we can add 181.49 plus that time that we had here, 60 seconds, which was the 1 minute. So we could add 60 seconds to that and come up with 241.49 seconds after dropping from the helicopter. Okay. Let's go ahead and take a look at our next example. A 400-pound object is released from rest 500 feet above the ground and allowed to fall under the influence of gravity. Assuming that the force in pounds due to air resistance is negative 10 v, where v is the velocity of the object in feet per second, determine the equation of motion of the object. When will the object hit the ground? Okay, using our equation for motion, we had mass times dv dt equals mg minus bv. Of course, this was our force 1. This was our second force. Now, what we notice here, though, is we will need mass. And this mass is going to go ahead and be the weight divided by the gravity. And I'm going to put a little star over here because what we normally have is F equals mass times acceleration. Now we have the weight equals the mass times the gravity. Okay, and here this mass is going to be in slugs when our gravity is 32 feet per second squared, and when we have the weight in pounds. Okay, so we could say that 400 is going to be equal to our mass times 32. We'll just go ahead and use 32. So the mass is going to be 400 divided by 32, which is going to be 12.5 slugs. So we'll go ahead and use 12.5 slugs, and then we have our dv dt. And now let's look at our two forces. Our mg was equal to 400, and then we are given our second force, which is our air resistance, as negative 10V. So we can go ahead and solve for dv dt, dividing each term by 12.5, and we have 32 minus 0.8 V. We also note that the object is released from rest, so our initial velocity is equal to 0, and so now we have our IVP, and we'll go ahead and separate those variables and integrate. Let's see what we have. We have 1 divided by 32 minus 0.8 V dV is equal to the opposite of dt. Oops, that should just be dt. And solving that, we have integrating both sides. We have the natural log of the absolute value of 32 minus 0.8 V, we do need a negative, is equal to t plus a constant. And we can just continue on in this fashion. And we will have to have a 0.8 here, and I can throw that negative down there. And then we can have the natural log, 32 minus 0.8 V is equal to negative 0.8 T plus constant. And continuing on in the same manner, we have the absolute value of 32 minus 0.8 V is equal to CE to the negative 0.8 T plus or minus both sides, removing those absolute values, and then we have the opposite of 0.8 V, dividing both sides by a negative 0.8, we come up with a positive 40, and of course another constant. So here we have V of t. Now let's go ahead and use our initial condition, V of 0 equals 0, to find C. So we have 0 equals 40 plus C e to the 0, so C is equal to 40. Therefore, V of t is equal to 40 plus 40 e to the negative 0.8 t. And we could also simplify that if we wanted and just say that V of t is equal to 40 times 1 plus e to the negative 0.8 t. So now, in order to find x of t, we could go ahead and just integrate v of t. So we will integrate v of t to find x of t. And so doing that, we have x of t is equal to the integral of 40 times 1 plus e to the negative 0.8 t dt. Let's go ahead and have our 40 on the outside. And we have 40 multiplied by t plus 1 divided by 0.8 e to the negative 0.8 t plus a constant. So we have 40t plus 40 divided by 0.8 is 50 e to the negative 0.8 t plus a constant. So we are going to go ahead and use our initial condition x of 0 equals 0 to find, and I should probably have said d. And so doing so, we have 0 equals 40 times 0 plus 50 e to the 0 power plus d. So d is going to be equal to negative 50. Therefore, x of t is equal to 40t plus 50e to the negative 0.8t minus 50. And that will be in feet. So that would be the location in feet at any time t. Now, we do need to see when the object will hit the ground. I am definitely out of room here, but I could just move that over. And so let's talk about when the object hits the ground. See if I can just make a horizontal line here. So when the object hits the ground, we will have x of t equal to 500. So we can go ahead and set x of t equal to 500. And as you can see here, we could ignore this term and we could come up with t. We'll go ahead and have 550 equals 40t. Let's keep going over here. So t is going to be 550 divided by 40, which is going to be 13.75 seconds. And so we do ignore the exponential term since that term is negligible when t is close to 13.75 seconds. Okay, let's look at our next example. If we're talking about the previous example, but the object is released from rest 30 feet above the ground instead of 500, when will it strike the ground? So using this same equation here, we now have 30 equals 40t plus 50e to the negative 0.8t minus 50. And we will end up with 40t plus 50e to the negative 0.8t is equal to 80. Now, note, if you ignore the approximation is incorrect. Okay, so this t occurs, you could say, somewhere on the interval 1 to 2. And so this cannot be ignored. Now, we are going to have to solve this, but we will have to use Newton's method to solve this equation. So what we have is g of t equal to 40t plus 50e to the negative 0.8t minus 80. And we'll go ahead and find g prime. I'll go ahead and do that right under it. And so we have g prime of t is equal to 40 multiplied plus 40e to the negative 0.8t. So let's use an initial guess. And that would be t1 equal to 1, and you could see that. And so we would have t1 equal to 1, and that gives us g of t1 about negative 17.53355. And in continuing in the same fashion, t2 would be 1.79601. And that's giving us g of t2 approximately equal to 3.72461. And t3 equal to 1.67386, giving us g of t3 approximately 0.05864. So we are getting closer. We come up with t4 to be 1.67187, and that gives us g of t4 approximately 0.000017. So therefore, the object will hit the ground approximately 1.67 seconds after approximately 1.67 seconds. Okay.